Recording is rolling. It is Tuesday, March 4th. So before I get into lesson today, reminder about SATs coming up in 2 days. So most of you guys, of course, are taking the SAT, and that information is on Google Classroom where you're supposed to go to test. Not everybody's taking it. The SAT is going to be in this room, so there's going to be relocations. And guys, here's my class relocations for my first 4 classes. The SAT should be over by the end of period 4. Now, maybe you're wondering about all your other classes. Where are all my other classes relocating? So that is on Google Classroom. So what have we got in Google Classroom? Oh, let me get back to that. All right, we're back. Here we go. So here's what's on Google Classroom this week. I got a volunteer hours opportunity if you're interested in that. Got my updated book. Oh, here's SAT relocations. Well, actually, this file is relocations. This other file tells you where you are testing. And then here's well, yesterday's class video here. All right, so everybody good with what's on Google Classroom so far and SAT? What you doing? All right, so that takes care of that. All right, so today we're getting to refraction. Right before I get into that, we give you guys a recap of what you guys saw yesterday. Yesterday, you guys saw a reflection. So we're talking about mirrors. So we started out very simply with a flat mirror, so like a plane mirror. And we're looking at this law of reflection. So the angle of reflection matches the angle of incidence. Now, that's true regardless of if it's a plane mirror or not. Right? Here could be a convex mirror, like a mirror ball. And we're saying, suppose you shine a laser light that's like parallel to a line that could go through the center. It's going to bounce off in such a way that it could align with this focal point. And this focal point is half the distance to the center. So the focal distance is half of the radius. Right? And we use that to make all these ray diagrams. You guys remember all these ray diagrams make? Okay. So here's a plane mirror. And oh, look, your image, your reflection shows up exactly on the opposite side for a plane mirror. That would be true. Right, then what if you look at the backside of a spoon, like a convex mirror? You always show up really tiny on the backside of a spoon. While we were doing ray diagrams, we were also checking with this equation, image location. So 1 over the focal length equals 1 over distance object equals 1 over distance image. And we ran a bunch of those equations yesterday, but they were all aligning with the story from the ray diagrams. So it's the same story from 2 different points of view. We had the diagram version and the algebra version. Same answer. We'll tell you where the location of the image is. Okay. There were also these concave mirrors. So that could be like a cosmetic mirror. Right? This mirror has a little bit of concavity to it. So if you put your face really close to the mirror, oh, it blows it up real big. And if you get far away, you might end up possibly with a real image. Kind of like, is that floating pig going around? Yeah, I see it over here. So there were a couple of parabolic mirrors just like this, and it created a real image. It looked like that pig was like floating above. You guys remember all that, right? Right. Also, modern day telescopes, like for example, the Hubble telescope is one of many that involves mirrors, and they have these concave mirrors in them. Right? All right, so that's all a recap from yesterday. Right, today we're going to switch from reflection to refraction. So what is refraction? That is this right here. You guys ever put a straw in a glass of water and it looks all bent out of shape? Okay. So, of course, the straw isn't really bent, but the light is refracting somehow to make it do that. So what's the story behind that? Switch over to Paul Hewitt. Gonna tell you guys.
Inclined plane. And I got some wheels. And I'm just going to roll the wheels down the inclined plane. All right. What I'm going to do is I'm going to roll the wheels from a nice smooth sidewalk onto a rough piece of material. It's almost like wheels rolling along a sidewalk into the grass. Or light coming down and interacting with the material and slowing down. If I roll them at an angle, did you see it bend? It came down like this and then bent. Let me put that on the board. My wheels are coming down in this direction, and they're coming from the smooth surface to the rough surface. When the wheels get to the rough surface, what happens to the speed of the wheels? Slow down. You know why they slow down? Because there's an interaction with the wheel and the material. Let's suppose it's like the little pieces of cloth on the towel, or maybe it's like blades of grass on a lawn, okay? There'd be some interaction, so this part would slow down. But what happens to this other part over here? It continues going quickly. So what happens? It sort of kilters. And so what happens is it goes like this. When both wheels get in there, they're going the same speed and they continue at a straight line. So there's no mystery as to why the wheels will kind of bend over, is there? I mean, if you can move along like that and something's on the way, won't you angle like this? I mean, part of it's slow. Well, guess what behaves the same way? Light waves. When waves of light come from above, say hit water. Maybe the waves of light are coming from the sun. Like that. We got a ray coming down like that. Incidentally, it turns out a light ray and the wave fronts that represents, these are like the crests of waves. Think of water waves, yeah? Right angle in here, gang. Always a right angle. See, even the axis of a wheel and the direction in which it's traveling, right angle. Okay. So what happens over here? These waves of light come down. And when they hit the water, what happened to the speed of the waves? Oh, you don't know that. Well, check your neighbor. They somehow go faster. What's the answer, gang? They slow down. Okay. The waves slow down. So what happens? They bend. And they sort of bend like this. And they get closer together. So the wavelength gets a little less in here, but the frequency of the wave stays the same.
Ooh, so we take that model exactly. It's a good model. So here's air on top, here's water down below. Right? And let's say you got a single ray of light. We're just following a ray of light. You guys have some lasers, so it's gonna be a connection later. Okay? And notice it's coming out on some angle. Right? Now, do you guys remember this equation right here from a few weeks back? Can you guys read this equation? What does this equation say? What is equal to what times what? So it's your wave formula. Velocity or speed velocity is equal to wavelength times frequency. Ah, there you go. That's it. Okay. Now, okay, so here's your light rate, which is really like a transverse wave. So if you go crest to crest, that distance is some wavelength, right? I can measure that. Say, what's that crest to crest length right there? Okay. Now, when the light hits the water, it does slow down. Okay, now you're messing with this equation. If you slow down, so you're decreasing the left side, well, you have to decrease the right side to compensate. Okay. Now the frequency stays the same because the frequency of these crests leaving the air has to match the frequency of the crests entering the water. It's the same. Okay. So leaving the air, it's like blip, 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 blip. Entering the water, it's like blip, 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 blip. It's the same frequency. Okay. So actually the proportion that the speed decreases by, the wavelength decreases by the same proportion. You guys that? Okay. And that's going to lead exactly to the next poster, which is you can say, how much does this bend? Okay. And we're going to measure that angle with respect to a normal line. You see this dashed line going vertical through the paper? Guys, everybody look up here? Guys, everybody look up here. Otherwise you won't know what's going on later today. Guys, if you're following everything I'm saying, it's going to make the lab, the last half of the class today, a lot easier. Okay. So I need whatever surface this is, like horizontal, I need a normal line, in this case vertical, to measure the angles with respect to that. And you guys know how to measure angles. I got a protractor. So I can zero out one of these and measure an angle. Is it? Right? And then I can measure this little angle down here. It's going to be like a little skinny angle down here. Okay. And the relationship between those angles, this is called Snell's law. Right? You can do some geometry and prove this whole thing, but it works like this. Right? And so n1 sine theta 1 equals n2 sine theta 2. And look, my theta 1, theta 2 are with respect to that normal line, just like I was showing you guys. Right? Now, what's the ends? The ends is something called index of refraction. Here, I'm going to spell this out. So, n equals index of refraction. And I put in this box down here, I said equals C over V. Right? And I think probably most of you guys can figure out what that means. Because what does lowercase c mean in physics usually? The speed of what? Speed of light in a vacuum. Speed of light in a vacuum. Ah, right. And this v, could that represent the speed of light inside the what? The water down here, right? Or later on today, when you guys do the lab version, this may be inside whatever glass piece you have. Maybe you have a glass piece on your desk, right? It's got something like that, right? Which is going to be what, faster or slower than in a vacuum? Slower. Therefore, should this index, are you guys ready for a logic question? Should this index for refraction, what makes more sense? Should this be more like 0.8 or 1.2? What makes more sense? Yeah, like 1.2. How do you know it has to be bigger than 1? How do you know this fraction has to be bigger than 1? Because the speed of light in a vacuum is as fast as anything can go in the whole universe. And the speed of light inside water is going to be slower than that. Yeah, so this could be maybe 1.2, 1.3, 1.4, 1.5, 1.7, 1.9, but it has to be more than 1. Okay? Is that right? And then and actually in a vacuum, it would be exactly equal to what? What's C over C? 1. Yeah, is that right? So actually, let's try this for water. Let's say I want to know what is the index of refraction of water. So I take my protractor, I measure this angle right here. Right, so say I zero out one of these and get the normal line, or I could zero out the normal line and find the ray. However, I do it. Let's call this about 40 degrees. Okay, could that be about 40 degrees right there? So I'm going to set up Snell's law, which is right here, right here. So I'll do n1 times sine theta 1 equals n2 times sine theta 2. Right, you guys get that? Right. Now, for this n1 on the side of the air, I'm going to say the index of refraction of air is really, really close to 1. It's like 1.008, something like I think, but I'm just going to call it 1. So just light refracted a little bit and going from a vacuum of space into the atmosphere. Yeah, a tiny bit, but right. Then sine, I'm going to put 40 degrees right here. Remember where I got 40 degrees? I got it by measuring this angle right here with a protractor. Okay, guess it? With respect to this normal line, which you guys are going to do later today. Okay? Then let's say I take the protractor and measure this theta 2, and suppose I come up with 29 degrees. Okay, so where this theta 2 is, I'm going to put 29 degrees. Okay? And then this N would represent the index of refraction of water. So put a little subscript W for water. Okay? Could you guys solve for W or solve for that index of refraction of water? Can you guys do that? Okay, you do that? Okay. Go ahead. So all you do is do 1 times sine of 40 degrees. Make sure, of course, your calculator is in degrees and not radians. So we're in degrees today. Okay, divide by sine of 29 degrees. Okay. I'm getting index of refraction of water is, where is that? Whoops. There it is, 1.33. Okay, that actually is about the textbook value of the index of refraction of water. So what that means is when light hits water, it slows down by a factor of 1.33. Okay, you guys get that? Right, you guys get so far? Good so far. Right? Right. And therefore, it bends like this much. Right? Now, you could change the angle of the laser, and I'll call that the angle of incidence, and the angle of refraction is always going to change too. Right? But it's always going to play according to this relationship, the Snell's law, where the index of refraction of water is always going to come out to 1.33. Okay? All right, you guys get so far? Right, so let's flip over to a couple of videos. I can show you guys this in motion. Snell's law. Right. Now, I have a triangle glass piece. Some of you guys also have triangles like I do. Some of you guys have this semicircle looking glass piece. And what's really convenient about the semicircle piece is, you can see it's like halfway through this video, right? You guys notice if you shine this light right at the center, right at the central node, the light will refract, going from the air to the glass. It does bend, it refracts, right? But when that light emerges on the curved side, isn't it always going to be perpendicular to that curved edge? As long as this is part of a circle, that would be true. Therefore, it doesn't actually bend again. So it only refracts basically once, which is on this flat side, right? And you guys see it has all these protractor marks, all these angles from 0 to 90 degrees on both sides. Is that right? And notice the angle that he's measuring with respect to. Do you guys see? I don't know if you guys can read it, but even if you can't, I bet you can figure out what this says. Guys, this line is labeled what? Starts with an N. No. Normal. As in perpendicular. Perpendicular to what? Perpendicular to this flat side right here, where you're going from the air to the glass. Do you guys see that? Right? So I'll model this with you guys too, and then have you guys do this. Right? Whatever side you're shining the laser light into, right? You need that flat side, and then take the protractor, measure 90 degrees, and you're measuring all the angles with respect to that normal line. So like right now, do you guys see this is shining in at, what is that? Does that say 50 degrees, I think? Is that that's a 50-degree angle? You see that? Right? Now, there's a few things going on. I mean, there's a little bit of reflection. We're not going to care about that today. Do you see some refraction at about 31 degrees? Do you see it? About 31 degrees? Hey, if you know this incident angle, which looks like about 50 degrees, and you know this refracted angle, which is about 31 degrees, is there enough information there where you can calculate the index of refraction of that glass? Yeah, there sure is. In fact, it's exactly what we just did, except with different numbers. See, I did it for water. I have 40 versus 29 degrees, and I got the index of refraction of water. Right? So you guys can do that for a glass. You guys can do that later today. Okay. Oh. Now go back to this video though, because there's something else I want to point out, which is, do you guys see as this video goes on? Right. So this angle of incidence is getting bigger, bigger, bigger. Okay, so it's 70 degrees now. He's going to hit 80. He's going to go towards 90. Do you guys see that the angle of incidence is growing faster than this refracted angle? Right. In fact, guys, what's the biggest angle this angle of incidence could possibly be? It can only go up to how big? 90 degrees, right? Maybe like 89.9 degrees. We'll call it 90, right? But this refracted angle, isn't it kind of petering out around 40 something degrees, right? Do you think this refracted angle could go to 50 degrees? Yes or no? Who says yes? Who thinks, oh, I think this refracted angle could probably hit 50 at some point? Who says, no, that's never going to happen? Yeah, I think you're right. I see a bunch of hands on the second option. Yeah, that's never going to happen. It's probably not going to get more than about 42 degrees, I think. Right, if you look here, we're close to the end of this video anyway, right? But there's okay, that's about as far as you can go. You guys see 85 degrees, right? I see a really strong reflection building up. Ooh, so like if I rewind a lot, I hardly see any reflection there, but near the end, right? We see some really strong reflection. No, I don't care about the reflection today. I just care about the refraction, and it's really weak. You guys see that really weak refraction? It's about 42 degrees, right? Guys, that 42 degree angle, it has a name. It's called the, does anybody know or have a guess or looking at some posters? The what angle? What could that be? The what angle? Starts with the C. It's called the critical angle. It's called the critical angle. You guys see that critical angle? Okay. Now I got another video where he shines the sun backward. Oh no, not that one. Let's do this one. Not that one. All right, here we go. Right, so same thing but backwards. Hey, look, now he's shining in the light on the curved side. Look at that. Now he's still aiming for the same point. You guys see this node point, like the center of the circle it would be, right? But look at that. Now the refraction is growing faster than the incidence because he's shining in the other way, right? It's just the same thing, just the opposite way, right? Who can tell me, guys, how far can you go? Like, what's the maximum angle of incidence before this refracted angle goes to 90 degrees and it doesn't refract anymore? 42 degrees. Let's see. So scroll ahead a little bit. I think I passed it. Right. Bam! Right there. Do you guys see that refraction? Go all the way flush to 90 degrees. And now the refraction is gone. And it's all reflection. That's called total internal reflection. What angle did that happen at? See, hey, it's 42 degrees. Look at that. You guys see this angle right here is 42 degrees? Right? That's the critical angle. You guys see how to get the critical angle? Right? Actually, there's two ways to get the critical angle when you guys do this lab today, which you guys are about to do. One way is to get it empirically, which is like this. You just change the angle of incidence until it goes from refraction to total internal reflection. Right? You can also calculate the critical angle using Snell's law. And here's Snell's law. You guys see a poster hanging in the room that has a pencil on it, just like this one? You guys see this poster hanging right here, right? This is going to be a very valuable poster today because you can use this equation probably more than once today. Okay? Right, but I think I got one more poster though. Yeah, here it is. Here's total internal reflection. You guys see this little fish down here? You guys think this fish is sending out like a billion different light rays all different directions? And I have 4 of them mapped on this poster. Okay, so if it goes straight up, just go straight up. If it goes to some angle, okay, it'll refract. Like these are different angles here. It'll refract a little bit. But at some point, that refraction goes to 90 degrees. And when it does, this is called what angle again? The critical angle? Actually, that would be the critical angle for this case, wouldn't it? Right. And I bet water has some known critical angle, right? Right. And then everything after that is just total internal reflection. Right. So I bet this fisherman is having a real hard time seeing this fish. And if he sees the fish at all, right? Let's see, how can this fisherman see the fish? Can he look straight at the fish and see the fish? No. Right. I bet there's a ray of light that goes maybe right about here, and it refracts and goes bam, like right into his eyes. So he's looking this way. He says, aha, I see you, fishy, and you're right over here. And keeps casting his line like over here, thinking the fish is over here because he's following this light. But really, the ray came from down here. Okay. So even though the fish is deep in the water, he thinks the fish is near the surface, even though it's not. Okay, so there you go. All right, so let's go back to I had some math started here. Okay, so I was playing off this picture. I was saying if this angle was 40 degrees and this angle is 29 degrees, we got all the setup and we got the index of refraction of water. You guys got that? Okay. Okay. Now, the other thing I want to find, remember this is index of refraction. The other thing I want to find is the critical angle. I'll call that theta sub c. It's critical angle. Right. That's the other thing I want to find. Now, of course, you can find it empirically. Just move the laser around until it goes to total internal reflection. Or you can use Snell's law, which is also right here. Snell's law. So let's go here. I'll label that Snell's law. All right. I'll just rewrite it. N1 times sine theta 1 equals N2 times sine theta 2. Okay. Now let's say on the side of the air. I'll call that side 1 on the side of the air. Okay. I forget if I told you guys or if you can figure it out. Do you guys have a pretty good guess, or do you guys know what is the index of refraction for air? 1. Oh yeah, actually we did that. We did that right up here. Okay, so I'll call it 1. Okay. Now, if I'm trying to chase down the critical angle, which could be on the side of the water, okay, whatever this critical angle is, that's going to make the angle on the side of the air go to what angle again? 90 degrees, right? So in place of this angle on the side of the air, I know because it matches this index of refraction, I'm going to put 90 degrees. Then over here, I know what the index of refraction of water is. Does anybody else know? What is the index of refraction of water? Aha! Right here, 1.33. We found that already. So after you find the index of refraction of your glass piece, then you can do this process I'm about to do, or I'm in the middle of doing right now, to find out what is the critical angle. Can you solve for this theta c right here? Can you guys do that? Here, I'll give you guys a try, and I'll solve that off screen. Let's see if we get the same thing. All right, I got the answer on my calculator screen. All right, how about you guys? All right, who knows? What is the critical angle for water? What's the critical angle for water? All right, who's got it? How about now? Here, give you guys a couple hints. Guys, what is sine of 90 degrees? 1. It is. Okay. I think about unit circle. Just start at 0 degrees and go around 90 degrees. Sine tells you how high you are in the circle, which would be 1. Okay, so this is 1. Okay. All right, here's the other hint. How do you extract an angle out of a trig function? Because that's what you're trying to solve for. You have to apply a what? Inverse sine. Aha! Right? Put it all together. I bet you guys can get it now. So who knows? Who knows the critical angle? Who's got it? Yeah. What you guys say?
0.015.
I wonder if you're in radians. I'm looking for some number of degrees, right? Degrees. Okay. Here, let's do this. So this, I know all this is equal to 1. I can divide out 1.33. So this is 1 divided by 1.33 is equal to sine theta c. Right. So then I have to take the inverse sine, and I did that right here. So I did inverse sine 1 over 1.33. I'm getting 49 degrees basically. So here, I'll put that right here. So theta c equals 49 degrees. Okay. That's the critical angle for water. Okay, you guys get that? Okay. So let me rewind a little bit and do a little bit of recap. What that means is if you're this fish down here, if you're beyond 49 degrees, if this angle turns to 49 degrees, then anything beyond that, the light's just going to total internal reflection, and it's not going to refract at all. It never goes above the ocean line, right? Right. And any bit of fish that this fisherman sees, he's going to see emerge from beyond 49 degrees, so like somewhere over here, right? Maybe like 40 degrees or something like that. Right? Okay. Oh, what else? Okay, and how do you get that? So you can either change the laser light until it just moves to 90 degrees, and you can find out the critical angle empirically, You can find it empirically, or you can apply Snell's law, and that's what we did here. Now, using the Snell's law method, first you have to know what is the index of refraction of the material, and you get that by finding an incident ray and a refracted ray for the air and for the glass piece. Okay, all right, you guys see that? All right, any questions so far? Any questions so far? Okay. All right, so I think it's gonna be lab time. Lab time. So, guys, find a page of paper. I'll have you guys turn this in right into class. Put your name on your paper. So everybody's got their name on the paper. Call a Snell's Law Lab. Snell's Law Lab. Okay. And your goal today is to find two things. Number one, what is the index of refraction of the glass? And okay, so you'll get n equals something. You might have to take some measurements, do some math, and then eventually figure out the index of refraction of the glass. And the follow-up question you're trying to figure out is, what is the critical angle of the glass? All right. So that could be theta c for critical angle. That's going to be some number of degrees. Okay. Now again, once you know what one of these answers is, the other becomes locked in place. Like there's some critical angle that's associated with every single index of refraction and vice versa. Okay, so if you know one, you can figure out the other. If you go through Snell's law, which I just gave you guys some notes a couple minutes ago. Okay. So here, I'll do a trial run with you guys. So there are different shaped glass pieces. Some of you guys have a triangle like I do. Some of you guys have a semicircle piece, which I showed you guys the video for. And so regardless of which piece you have, you'll have seen an example. So I'm going to trace that glass piece. I guess I just put a line all the way around. Okay. So lock that in place. Right. I'm going to shine in a laser light. Right. So I got my laser going right here. The laser going. Yeah, there you go. Right. And I'm looking for a refracted path. Right. You guys see this bead of light? See, I can kind of shift the laser up and down. I can follow that path of light on the paper. You guys see that? They shift this up and down. Right. It goes right here. Yeah. So like coming out. Okay, coming out right there. Okay. Now, guys, you're not looking for reflections, and there's plenty of reflections going on. For example, okay, I can see it much better in front of my face than on the camera. But it kind of shows up on the camera. Okay. I don't know. Can you guys see a bead of light that reflects right away? So I don't care about that. I also see some light emerging over here. Does that show up on the camera? Yeah, a little bit. Right. I don't care about that because that reflected off the surface. I don't care about any reflections. I'm looking for all refractions. You should switch to pink ink. So I'm going to trace out a refracted path. So for example, here's a bead of light going in this way right here. This is bead of light, bam, right along that line. Bam, right there. It's going to refract here, going from the air to the glass. Then refracts from the glass to the air. And it emerges on this side right here. Right. Here's exactly a path. You see refraction followed by refraction and emerges right there. Right, so turn the laser off. Right, put that to the side. Right, let's get that path. So this laser light, I was shining it in exactly that direction, and it emerged on the other side exactly over here. Now, in the middle of the glass, it had to have gone from here to here. So that was the path of the laser light. You guys got that? That's the full path. Bam, bam, bam. There's two refractions from the air to the glass and the glass back to the air. Right? You can play off either one of those points. I'm going to take this point where I was shining in the laser light. Okay. Now, guys, how do I measure my angles? I'm measuring my angles with respect to a what kind of line? A normal line. Ooh, which I don't actually have drawn yet. I need to draw a normal line. So protractor, I'm going to put the node of the protractor right on this point where I'm measuring all the angles with respect to, and go to 90 degrees. Put a little dot right there. And dash off a normal line. So this line right here that I'm dashing off is perpendicular to the space where I was shining the laser light in. Okay. I'm measuring my angles with respect to that normal line. Look at that. Okay. Now some of these lines, like this line is really short, so I'm going to extrapolate it, make it longer. So if it had just continued, or if this glass was like really, really big, like table size, the light would have continued along that dashed line right there. Okay. So what are my angles? Here's my angle of incidence right here. I'll call it theta A for the side of air. And here's my angle of refraction. I'll call it theta G for theta on the side of the glass. You guys see that? Okay. Now, what are these angles? Okay, so I can put this node of this protractor right on this point. I can zero out the normal line, and this incident angle, well, it'll sweep through. Now, look at that. Here, I don't want to give away too much, but just get the idea. You guys can measure angles, right? So that angle's so many degrees right there, right? Then I say, well, what's my theta on the side of the glass? I need this whole wedge right here. Is this whole wedge right here? Okay. So again, put the node on that point, zero out the normal line, and well, my extrapolated ray goes through so many degrees on this side. Okay, so now I have the angle on the side of the glass. Okay. Okay. Now the star formula today is of course Snell's law, which goes like here, I'll even spell it out again. Snell's law. I know N1 sine theta 1 equals N2 sine theta 2. Right? Now, here, I'll recap this whole process with you guys. So on the side of the air, what is the index of refraction equal to for air? Let's call that 1. Yeah, 1. This theta on the side of the air, it's however many degrees this is. That goes right there. The theta on the side of the, oh, sorry, well, the index of refraction of glass is what you're solving for in glass. Right? And theta 2 is whatever the angle on the side of the glass is, which is going to be a smaller angle. Right? Okay. So that'll let you figure out what's the index of refraction of the glass. You guys get that? After you get the index of refraction for the glass, there's two different ways you can get the critical angle. Now, one way is to shine the laser light so that you're going to like almost parallel to the face, like almost 90 degrees. Now, that's the empirical method. That's really hard to do it that way. Unless you have that semicircle piece, then you can do the same thing on the video. You can shine it on the curve side, and you can probably figure out this empirically pretty quickly. Okay? But the other way to get the critical angle is to set up the new Snell's law. So you take your N1 sine theta 1 equals N glass, which at this point you will have known because you will solve for it, times sine of some critical angle. Right? Or, well, this would be the critical angle as long as this other angle is equal to, see if you guys are following what I'm saying. What should this angle be on the side of the air to correspond to a critical angle on the side of the water? Theta air should be what? What's this angle right here? 90 degrees. If you plug in 90 degrees on the side of the air, then the corresponding angle on the side of the glass is the critical angle. Okay. And what's the very last algebra step to extract this angle? You have to apply a what? Inverse sine. Aha. Okay. So I think you guys got it all right there. Right. All right. So last minute here. The star formula today poster. You guys see this one's hanging up in my room, right? It's hanging up right in front of me. Right. You guys can refer to Snell's law. Other than that, I'm just going to leave all of this right here for you guys. So once you figure out the index of refraction of the glass and the critical angle, then turn this into the gray tray and you're good to go. Now, a lot of students have finished this today. Right? A lot of students have not finished this. If you don't finish this today, then at least measure your angles and then you can do the calculations tonight and turn that in tomorrow. And that's a wrap on the video.